All right, so this is Mr. Allison at Cornerstone Charter Academy. We are going to do a quick walkthrough on physics honors, quarter 3, assignment 11.2 in the 2020-2021 school year. Looks like this. It is in, that's weird. I wonder why I have 2 attachments. It's very strange. Okay, who cares? So we're gonna, one's a Word document and one's a PDF, that's why. All right, so we're gonna open this up and take a look at that. There's our PDF. We are gonna go, I'm gonna do this again, just like we did last time, because it actually worked. Woo-hoo. We're gonna go into the PhET lab here on this. And I know that I could just have this all open, but for some people, they might even have trouble getting to the lab. So now we're on PhET, and if this window was wider, if the window was wider, okay, well, if the window was wider, you would see a menu on the top. But as it is, we got to have a drop-down menu. And so you're going to click Simulations, and then you're going to go to Physics. And I'm going to move this over here to, whoa, that is a little bit weird. Oh, that, you know what, that's probably just lag because of the video recording software. All right, so we got this set up now. Okay, so this is all looking pretty good. All right. Okay, that's big enough to see. Alrighty. So now what lab are we looking for? Energy formed and changes. So we'll scroll down. Energy skate park. Energy forms and changes. There it is. So we'll click that. And then we'll click that to go into the lab, and then we'll start with the lab. Okay, so first of all, warm up. It says, what do the following terms mean? All right, so there's a difference between heat and temperature. Heat is the total energy. It's the energy of the system. Heat is the energy of the system. Temperature is a measurement of the average kinetic energy of the molecules in something. So if you picture, here's the easiest way I think to remember it. If you have 2 beakers, and one has this much water, and one has this much water, but this water is hot. That's hot water. That's why I guess I should have made it more like, I mean, not the water is red anyways. I was trying to do like fire color. Okay, so that's hot water. And then this water here is cool water. So those have different temperatures, but the same, they could have the same heat because these could have, they're going to have different temperatures because this one's cold, right? And this one's hot. But they could have the same heat because they could have the same energy. You just have the energy of you have the same amount of energy, but it's packed into a smaller space. So the average kinetic energy of the molecules is going to be higher because the space is smaller. So the temperature is the average kinetic energy, and the heat is the total energy. So these two could have the same amount of energy, but because the energy over here, the same amount of energy is in like, I don't know, I'm making this up, but it's like 3 times the amount of volume at least, right? Then that means that the temperature is going to be a lot lower. All right, so that's what that's about. Using your definition for temperature above, explain how a thermometer works to provide a visual representation of the temperature. So what happens with a thermometer? We might as well, it doesn't say to go in here yet, but I'm going to go in here anyways. So we're going to put the water right there. I'm going to drop that. Okay, so when you have a thermometer and you put it into a liquid, well, we'll put it in the liquid since we have the capability to put it in the liquid. So when you put the thermometer in the liquid, it's experiencing the crashing around of all those molecules, right? And so what happens is they crash around in the thermometer and they transfer their kinetic energy, some of it, to whatever liquid is in the thermometer until the average kinetic energy of the thermometer equals the water. Because once the energies are the same, then the energy is not going to transfer anymore, because we know by the second law of thermodynamics, which we already studied a little bit, is that energy always flows from hot to cool, or from higher energy to lower energy. It doesn't go the other way around. So the higher energy water flows into the cooler energy thermometer, to cooler temperature thermometer, until they both have the same average kinetic energy. And that's when we can tell what the temperature is, because the temperature is the average kinetic energy. So there, now the temperature is going up in the water. Okay. Thermometers in the past were filled with mercury, but most now are filled with alcohol due to safety reasons. Why do you think alcohol is used instead of water? And the answer is because water has a you remember this, water has a very high specific heat. And so water, it takes a lot of energy for the temperature of water to change a little bit. And so alcohol probably has a much lower specific heat. Let's look it up real quick. The specific heat of alcohol, let's see, it varies for different alcohols, because there are different kinds of alcohols, right? Let's see here. That's ethyl alcohol. So the specific heat, that's not. Does alcohol have a higher specific heat of water than water? That's what we're looking at. There we go. Let's just click on that link. Although it's probably looks like it might be a college level link. We'll see. Okay. Water has a specific heat of. So the thing that's confusing me is that our textbook gives specific heat in one. It's just a different order of magnitude. We have joules per kilogram of water to raise it, and they have joules per cubic centimeter of water, which is probably more right. Okay, so here's H2O, that's water. So the specific heat of water is right here, and it is 4.18 joules per cubic centimeter. And there's methanol, that's a kind of alcohol, so that has a specific heat of 2.53 joules per cubic centimeter. And then ethanol has a specific heat of 2.44. So 2.4, 4.1, it's not quite half, it's maybe 3/5 or so. So anyway, the reason is because alcohol has a much lower specific heat. So it takes less energy to change the temperature of alcohol. And you want the temperature to change because that's what makes the density change. The molecules all start bouncing around faster, and you want that to happen so that the fluid in the thermometer goes up. All right, so the simulator allows you to add the same amount of heat to different materials, okay? If you're able to measure the temperature of these materials as you're heating them, would you predict that each would have the same temperature changes? No, you wouldn't, because each material is going to have its own specific heat, which is the amount of energy it takes to change the temperature, right? And that's what we just talked about with alcohol and water. It takes a lot less energy to change the temperature of alcohol. And so the thermometer would work faster. It also wouldn't absorb as much energy because there's going to be a tiny bit, right? You're going to change the temperature of the water by putting the thermometer in it a tiny bit anyways. Okay, so here we go. I'm going to go over here and I'm going to reset that lab. It's all reset. Position the iron block. And again, what time it's, how much time do I have to do this? Because that'll tell me how fast I have to go. I have 15 minutes left to do this. So let's see. Position the iron block on one of the ring stands. So we'll pick that up and stick it on there. You can have energy symbols, and linking the heaters means they both move exactly the same. So they're going to give off or absorb the same amount of energy. The energy symbols just show you, you can look, as I add energy, you can see little energy blocks flowing into the iron, right? So that's what that does. Okay, so now we're going to reset everything again, put the iron block on there. Okay, click the energy symbols and begin increasing the heat under the iron. Describe what you observe. So you increase the heat, what do you see? Increasing energy. There's more energy in that iron block, right? Predict what you would see if you were able to measure the temperature of the iron block. Oh, were we supposed to put the brick block too? Put the iron block on a thermometer. Oh, we're supposed to have a thermometer on it to measure the temperature. There we go. You can drag as many thermometers as you want. Oh, what is that? That's the heat dissipating off the iron block, right? Because energy dissipates into the air. How about that? Let's see. And click the energy symbols tab. Okay, increase it. What do you predict what you would see if you were able to measure the temperature of the iron block and the brick block as you supply the same amount of heat? All right, so if you apply the same amount of heat to an iron block and a brick block, which do you think is going to have the temperature raise faster? So that's a question of specific heat. It kind of correlates to which one's more of an insulator versus a conductor. We're in electricity now. Conductors tend to heat up faster. Why? Because they conduct energy faster, right? So let's reset it. And now it says to put the iron block on one stand and the brick block on one stand, right? And we're going to put a thermometer on each one. And you can see the little triangle, the sideways triangle next to the thermometer turns to the color of the item so that you know that you've got it there. Click the energy symbols on, right? And then link the heaters. Okay, so now we got, oh, look at that, interesting. They are the same temperature, but the iron has more energy symbols in it, unless they're hidden in there somewhere. So the iron actually has more energy, even though the brick and the iron are the same temperature, right? So you would say the iron has, even though the brick and the iron blocks are the same volume and the same temperature, the iron has more heat because it has more energy, right? So now what's going to happen, do you think? What do you think is going to happen? Which is going to have the temperature raise faster? Here we go. Oh, forgot to link that. Oh, now I got to reset. Okay, fine, whatever. Boo. It only takes a moment when I don't have to talk through it, right? Link the, okay, the heaters are linked now. Okay, so the iron has more energy in it at the same temperature. Now the question is, what's going to happen to the temperature? We're adding energy. And it looks like the brick is heating up faster. I should have put these at exactly the same height so it'd be easier to see, right? There. So the brick heated up faster. The temperature on the brick rose faster. So the brick must have a lower specific heat. But the brick is also losing its heat more slowly. Very interesting. All right, increase the temperature on the blocks and observe and record the observations. Okay, so we already did that one, so let's just do it again. If you wanted to use these experiments to get quantitative observations and create a graph, you could test the variables, right? Okay, so the brick gets up to the top faster. Let's see what gets where they go as they go down. So you would create what would be the independent variable? That's the one you're controlling, right? That's the amount of heat you're adding. The dependent variable would be the temperature, right? Because that's what you're measuring. And the control, I don't know, who cares? Okay. So we're going to do the same comparison, only we're going to do liquids now. And which do you think is going to heat up faster? The water. Okay, so I'm going to try and put these very close together. So there we go. Now we can compare them easily, right? That makes good sense. See, you learn things when you do things. All right, so now we can compare them easily. So which do you think is going to heat up faster, the oil or the water? So now we got linked heaters, and we're gonna go like that. We start adding energy, and which heats up faster, the oil? The oil heats up a lot faster, doesn't it? Because oil has a lower specific heat than water. And you can also see, so water is holding on to the energy more. Okay, there we go. Now that water's probably getting close to boiling, that's why. Look how much difference in the energy they absorbed. All right, now this time we're going to repeat it with water and iron. So what are we going to see? There's iron. Which is going to heat up faster, do you think? Which has more heat right now at that temperature? Water does, assuming they're roughly the same volume. But which is going to heat up? Oh, I almost didn't put the thermometers in. So there's the iron. There's the water. All right, predict before I do this, or before you do it, I guess. What's going to heat up faster? Iron or water? Look at how much faster the iron heats up than the water. Wow, that's pretty cool. And the brick and the brick heated up a little bit faster than the iron. So it's going to heat up even faster, right? Interesting. Okay, so what does that experiment tell you about water? Oh, so what does it? I would say it tells you it's got a high specific heat. It takes a lot of energy to heat it up, right? Okay, specific heat capacity is the amount of heat required. How are we doing on time? We've got 5 minutes left. The amount of heat energy required to raise the temperature of a substance per unit of mass and for 1 gram, right? It's essentially a property of matter that describes the ability to store heat. Different materials have different specific heat capacities. Conduct research to find the specific heat capacity of water and iron. So that must mean look it up, because we don't have any, unless, let me go back, maybe there's the other sim has more gauges and stuff on it. Systems, nope, it's got to be that one. And so you have to go look up the specific heat capacity of water and of iron. You can look it up in your textbook. But that's going to be joules per kilogram to raise it. And if you look online, as we already did, that was joules per gram of water. So then 14, based on your observation and analysis from the above, what would you expect to see when you research the specific heat capacity for copper? So copper's a metal like iron, and you would expect, I would expect anyways, the specific heat capacity of copper to be something like that of iron, although I think that it's probably lower. And the reason is just because copper is a good conductor, so I think it's going to take less energy to heat copper, but I don't actually know. And the next question is for you to go look up the specific heat capacity of copper. And then you're going to say whether or not that, it says this means, and so what you're going to do is compare that. You should fill in that blank with a comparison of the specific heat capacity of copper to the specific heat capacity of iron, and what that means about which one takes more or less heat to raise the temperature of it. All right, clay bricks are used as building materials in construction. Do some research on specific heat capacity of brick, stone, concrete, and advise on what that means for society. Wow, that's a big question. So yeah, look at a few building materials, brick, stone, and concrete. Pick those 3. You don't need to do anything else unless you're interested. You could do more, but look up the specific heat of those 3 and which one of those actually takes more heat to move the temperature, because the more heat it takes to move the temperature, that's going to be like a better insulator, right? And let me just explain that to you real quick. So let's say if you have a barrier, let's say this barrier is brick, and then this barrier is concrete. Pretend they're the same thickness, concrete, and this barrier is stone, right? So you're going to have the idea of the heat rising, the specific heat, right? Because, okay, so on the outside in Florida, you've got a lot of heat hitting the walls, right? And when you build a building, you build it with walls, and then slowly those walls heat up. And as those walls heat up, I'm pretending the right of each wall is outside and the left of each wall is inside. So as those walls heat up, they start to radiate heat into your house. And so the higher the specific heat capacity, the better it will keep that heat out during the day. Now, there's more to it than that. There's another thing called thermal conductivity, which is how fast it transmits the heat through it. Also, there's other. So that's one thing. Actually, air is a pretty good insulator for thermal conductivity. Air pockets are decent insulation. The more air pockets you can form, the better. We're going to run out of time here in about a minute, so I better stop with my extraneous information. Oh, that's the last question. Okay, so an igloo or a snow hut is a type of shelter built out of snow, traditionally used by people of Canada's Central Arctic and Greenland Thule area. Conduct research to find out the specific heat capacity values of the materials that igloos are made out of. What are they made out of? Snow, right? Frozen water. And then explain whether these are an efficient choice for design of a home in colder climates. So what do you think in terms of, like, you got the specific heat capacity? Now, with regard to snow, that's good. So you can just look up the specific heat capacity of ice, or actually look up snow, because snow is going to be even less dense. It's going to have like air pockets in it. So maybe even look up snow and see what that is. And you can compare that to brick, concrete, and stone in terms of its specific heat capacity. And you decide whether you think it's a good building material, okay? So that's that. Thanks for listening. I hope this helps you, and get that done so your grade goes up. Bye.